Okay. Messy bed. It's okay. Let me see. Okay. So I think I can start now.
Okay, you have covered up to about Jacobson radical and near radical, right?
And radical ideals, prime ideals, things like that.
Mm-hmm.
Okay, should I start?
Yeah.
Okay. So today is June 2nd. So today there will be very little theory, but a lot of exercises. And we'll just introduce a new concept, which is the Zariski topology. And so this, unfortunately, I will have to assume some people have a background in topology, understanding what open sets are, understanding what a topology is, and compactness and Hausdorffness. So let's start. This is from the textbook, and it says, let A be a ring, X is set of all prime ideals. Of A. And then for each subset, let's say E of A, let V of A be the set of all P such that P is a prime ideal, and E is contained in P. Okay, so we have to prove some things. So the first question is, if I is an ideal.
I cannot see your screen, by the way. I mean, even though you're writing something, I cannot see it.
Did you see it before?
I can see your iPad screen, but okay, can I see your iPad screen again? So there's some block. Now I can see it. Yeah, please go ahead.
Okay, I had this issue in the past. Hopefully it doesn't happen. It's okay.
Got it.
So tell me if there's an issue.
Yeah, I will.
So if I is an ideal, so let's say generated by the set E, we have to prove that V of E is the same as V of I, which is the same as V of the radical of I. So how do we do this? So let's try to prove first V of E is V of I. Okay? So clearly, if P is a prime that contains I, then it contains E. So we also have that V of I is contained in V of E, right? And so that proves direction right to left. And now let's say that if P is a prime that contains E, then P contains I, because all elements of I are of the form R times E, where R is in A, the ring, and E is in E, the set. So if it contains every element little e, then it contains every element of the ideal I, because every element of I is of this form. Okay? So now how do we prove that V, I'm sorry. Let's actually, it's not of this form. It's a little bit, I'll say, actually, it's a little bit more like this. R1, E1 plus R2, 2, Rn, En, where Ri is in the ring and Ei is in E. And so clearly, if the prime ideal contains E, then it contains all elements of this form. And so then we have I is contained in P. So we are done with that equality. So how do I prove now that V of I is V of the radical of I? So now clearly we have V of I is contained in the V of R of I, because if P is a prime ideal that contains the radical, then P contains I, because I is a subset of the radical of I. It's just set theory. So now let X be an element. I'm sorry, let's start over by saying that let P be an element that contains I, and let X be an element of the radical of I. Then that means that X to the M is in I, but that's contained in P. So X to the M is in P. So that means X is in P. And therefore, P contains the radical of I. So we are done. So V of I is equal to the V of R of I. Okay, that's part one. Now let's prove part two. Part two is much faster. Part two asks you to prove that the set of prime ideals that contains 0 is all the prime ideals, and the set of prime ideals that contains 1 is empty set. But that's clear because all ideals contain 0, so all prime ideals contain 0, and also if a prime ideal contains 1, it can't be prime. It would not be proper. So we have an issue. Next, it asks if EI is a family of subsets of the ring, then we have that the set of all prime ideals that contain the union is the intersection of the set of all prime ideals that contain each EI. How do we do this? So again, this is a lot of it is set theory. So let P be a prime that contains the union, then clearly P contains all the subsets EI. So that means that if you're a prime ideal that contains the union of the EI, then you contain each of the EI. Okay? And so now what about the other direction? Now let's say P be a prime not in the EI. So that means that the union of the EI is not contained in P. So there exists some X in EI for some I such that X is not in P. So that means that EI is not contained in P. So P is not in V of EI. And so we are done with question number 3. And now let's do question number 4. Question number 4 asks you to prove V of I intersect j is v of I times j. Prove that this is equal to v of I union v of j. So how do we prove this? Let's start by proving v of I intersect j is v of I times j, first of all. So first of all, note that I times j is contained in I intersect j, because if you have x is in I and y is in j, then x times y is in I and it is in j. So it is in the intersection. So that means if P is a prime that contains the intersection, then P contains I times j. So V of I intersect j is contained in V of I times j. Okay, and so now let's prove the other direction. Let P be a prime not in V of I intersect j. So that means I intersect j is not a subset of P. So there is an element x in I intersect j such that x is not in P. How do we prove that P is not in V of I times j? I need to show that P is not in V of I times j. In other words, that I times j is not contained in P. So how do I find an element of I times j that I know is not in P? Note that x is not in P. That x that we said was in I intersect j. So that means that x squared is not in P because P is prime. And so x squared is actually in I times j. So P is not in V of I times j. So we are done. So these 4 exercises prove that you can actually make a topology using these sets. So let X be the set of all prime ideals of a ring R, of a ring A, let's say, and let and for each, let's say, subset E of A, define V of E as above, then the collection of sets of the form V of E form the closed sets of a topology on X. So X is a set of all prime ideals of a ring A, and so these V of E, these sets of the form V of E, are the closed sets of some topology. That topology is going to be called the Zariski topology. So they say Zariski topology on, I guess I'll say X, and so we'll say the topological space is called the prime spectrum of A, and we can also call it, denote it as spec of A. Okay, so that gives you an understanding of the topology from closed sets. Let's try to understand the topology using open sets. So that was question number 15. So let's skip number 16. It asks you to draw pictures of the spectrum of different rings. That's a nice exercise, but let's move on to more theory. So let A be a ring again. Let's say F is an element of A. Let XF denote the set of all primes prime ideals of A that do not contain F. So we need to prove a couple of things. We have to prove that XF is open. We have to prove that the set of the form XF, where F is an A, forms a basis of the spectrum of A. And we have to prove that intersections behave nicely. We have to know when, we have to know when an open set is the empty set. We have to know when the open set is a whole set. And we have to know when they're equal. We have to know if the space is compact. And we have to know when open sets are compact. Okay, so there are many questions here. We should solve them all. Let's start with number 1. How do I prove that the sets of the form X sub F are open? So X sub F is a set of all P such that P is prime. And let's say F is not in P. And then the complement is a set of all primes. P is prime. And F is in P. This is precisely V of F, which is closed by what we did before, by how we constructed closed sets. So question number 1 is done. Question number 2, how do I prove that these sets form a basis? So first of all, we need to prove that each prime ideal lies in a set of the form X sub F. So if P is a prime ideal, then we'll say that P is proper. And so X is not in P for some X in A. Thus, we have that P is in X sub X. And then let's see how to prove the intersection aspect of basis of open sets, but that's already the third question. So let's answer the third question. How do we answer this question? Why is the intersection of xf and xg equal to x sub fg? So let P be a prime in xf intersect xg. Then that means P is both in xf, so that means f is not in P, and P is in xg, so that means g is not in P. So by the fact that P is prime, so the product is not in P. So that means P is in x sub fg. So that's the one direction of set containment. Now if we let P be a prime that is not in x sub f intersect x sub g, then without loss of generality, we can say that P is contained in x. P is not contained in x sub f. So that means f is an element of P. So that means that fg is an element of P, and so P is not an element of x sub fg. So we have a nice behavior of the intersection of open sets. Let's move on to number 4. Any questions so far? Everything good? Okay.
Yeah, very good.
Okay. So how do I prove that a basic open set is empty if and only if the element f is nilpotent? So let's say let f be an A such that we have that xf is not empty, so there is a prime P such that P is in xf, meaning f is not in P. So thus f is not an element of all prime ideals. That means that f is not in the nil radical n. It can't be in the intersection of all prime ideals. So f is not nilpotent. It's good. Now, let's say that conversely, if xf is empty, then that means then all prime ideals contain f. So f is in the intersection of all prime ideals, P is prime, which is the nil radical, and so f is nilpotent. So that's question number 4. So we solved it. Let's move on to question number 5. So how do we prove that a basic open set is the set of all prime ideals if and only if f is a unit? So let's say let f be a unit, then clearly no prime ideals can contain f. So clearly all prime ideals are an element of X sub f. Let f not be a unit, then as we explained before, I think 2 weeks ago, then f lies in some maximal ideal. I'll say P. Thus, we have that P is not an element of X sub f. So X sub f is not all X. So that's the answer to number 5. So here's where things get kind of tricky. How do we relate the radical of f with the basic open set f? So I will actually have to look at my notes a little bit to resolve this. So first of all, let f and g be an A, such that, let's say, r of f equals r of g. I want to prove that x sub f equals x sub g. So it is enough to show that x sub f is contained in x sub g, because after you just switch the terms f and g, you will have solved it. It's the same thing. So let P be a prime that is contained in x sub f. So that means f is not in P. I need to show, NTS need to show that G is not in P. So first of all, if f is not in P and the radicals are the same, let's assume that G is in P. Let's assume G is in P by contradiction. So if G is in P, then the radical of G is in P, because let x be in the radical of G, then x to the m is in G, which is contained in P. But because a power of x lies in P, that means that x itself must lie in P, because P is prime. But we said that the radicals are the same. The radical of f is the radical of g. So that means that the radical of f is contained in P, but that means that f is contained in P. Here we have a contradiction, because we assumed up here that f is not in P. So we in fact proved that if r of f equals r of g, then that means x sub f is contained in x sub g. And I don't know why there's a difference between f and g. That's the same as just saying x sub g is in the x sub f. They're the same thing. Okay. So we proved one direction. Conversely, I want to say that, let's say, suppose x sub f equals x sub g. I need to prove that the radical of f equals the radical of g. So it is enough to show that the radical of, what did I say? I think I said, yeah, it's enough to show that the radical of f is contained in the radical of g, because f and g They're just different letters. Doesn't mean anything. So, so suppose x sub f equals x sub g, and it's enough to show that the radical of f is contained in the radical of g. So let x be an element of the radical of f. So x to the m is equal to a times f for some a and some integer m. And so that means that sorry, one sec, let me go backwards. So if P is a prime that contains F, then P contains x to the m. So that means P contains x. But then that means P contains x, and so P, sorry, one sec. So P contains, if P contains F, then P contains X. So also P does not contain G because of what we said up here. I'm sorry. It does contain, sorry, P does. So P contains G. Sorry, so every prime P that contains F also contains G. So if you have an element of the radical of F, sorry, let's start over.
Okay, it's fine.
Yeah, let's just start over.
Yeah, let's do step by step.
So it's enough to show the radical F is contained in the radical of G. If we let X F so let, again, X be an element of the radical of F. So let's say X to the M equals AF. Okay, that's no problem. Let P be a prime that contains F. P is a prime that contains F. So P also contains X because of X to the M is in P, so X has to be in P. So that means that if we need that Q be a prime that contains G, I need to prove that X is contained in Q. If we say that,
yes, then you're done.
Yeah, if we have that if X is not in Q, then Q, does not contain the radical I'm sorry, I'm ruining my notes. It's okay.
It's fine. Q does not contain X.
I'm sorry.
We didn't use the assumption yet.
Yeah, we didn't use the assumption. You're right. Okay, so actually, so P contains X. Actually, X is an element of all prime ideals that contain F. Okay, so X is an element of all prime ideals that contain F. Let Q be a prime ideal that contains G. If we prove that X is in Q, then we are done. So assume X is not in Q. And so therefore, that means that, I think that means that, I don't know why I'm having so much trouble with this.
It's fine.
All right, let's just skip this.
Yeah. We can go over next time if you want.
Let's go over it next time. I'm having some trouble. But the next question is very good. I'll fix it next time. I'll say next question.
No worry.
Yeah. Sorry, Gunhi.
No worry.
So let F be an A. Prove that how do I prove that the basic open set XF is compact? So how do we prove this whole set of prime ideals is compact in the Zariski topology? So let first of all XF be contained in a collection of open sets UI. But each UI is just a collection of open sets XG. So that means XF is actually just contained in a set of open sets XFI. How do we get a finite subcollection of this open set? So if we have this condition here, then what does that mean? So if that means that let, first of all, J be the ideal generated by all the Fi. So if P is a prime ideal in XF, then P is in X sub Fi for some Fi. So that means that if P is a prime ideal that does not contain F, then P does not contain one of the Fi. If you use the contrapositive, so that means that if P contains all the Fi, then P contains F. That's what that means. So that means if P contains J, then P contains F. What does this mean? So that actually means that the collection of all primes that contain J is a subset of the collection of all primes that contains F. That means there are more primes that contain F than there are primes that contain J. That means that the radical of F is contained in the radical of J. So this is an extremely important part of this question. This is hard to kind of understand where to start, but if you kind of relate these prime ideals with the radical, just these open sets with the radical of an ideal, then it makes more sense because we have more things that we can do with radical ideals. So we have that the radical of F is in the radical of J, but note that also the F is an element of the radical of F. So that means F is in the radical of J. So that means that f to the m is in J, and so that means f to the m is, I'm sorry, it's in, oh, I'm sorry. For some AI in A and some finite subcollection of the Fn. So, so that means that, what was I trying to say? Yeah. So we have to try to find a finite subcollection that covers this set. So I claim that X sub F is contained in, I'm sorry, X sub F1, X sub F2, F sub Fn. So how do I prove that? Let's just do the opposite. So I'm going to say that if P is not in, this union, I want to prove that then P is not in X sub F. So this is clear because if P is not in that union, that means all the Fi's are in P. These finitely many Fi's, they're in P. And so then that means that F to the M is in P, and because P is prime, then that means F is in P. And so we are done. So we have proved that from an infinite collection of open sets, we can find a finite subcollection that covers it. Okay? Mm-hmm. And so, yeah, I think that covers that question.
Yeah. Yeah, very good.
Okay, and so a corollary is that X being X sub 1 is compact. So we have a topological space that we endow on the set of prime ideals, which is compact. This is very nice. And so for the final question, how do we prove the last question? Number 8, we already proved. Number 9, so an open set is compact. An open set of X is compact infinitely if it is a finite union of sets of the form XF. So let's go this way. So if it is a finite union of such sets XF, each XF is compact. And so that means a finite union of them is also compact, just from basic topology. And so that proves one direction. The other direction is that let U be an open set of X. U I can write as some collection of XF. I'll say this. And so because U is compact, there must be some finite subcollection. That contains the U, and so we are done. I'm sorry. And therefore, there is in fact a finite subcollection except X sub Fi that equals U. Okay, would you like to do one more question or stop for today?
Up to you.
How long have we done this? 50 minutes?
It's also up to you.
Let's do
more, or you'd like to start from next time?
let's do this same chapter next time, and we'll do a little more questions, but let's stop for now. Okay.
Got it.
Sorry for the mistakes, but I will improve it next time.
It doesn't matter at all. And thanks for lecturing today also.
Yeah.